So we have 2 more lessons to cover. This lesson is called Equations and Graphs Part 1. Tomorrow we're going to do Equations and Graphs Part 2. There's a little something right at the beginning of this lesson that is not directly connected in terms of how we solve the problem to equations and graphs, although that little part at the beginning can be solved by looking at graphs. Okay? It's just not necessary. Today what we're going to be doing is putting together everything we have learned about factoring polynomials and the fact that the factors lead to the x-intercepts, but we add another layer. So we're going to solve polynomial equations, and then we're going to be looking at the relationship between x-intercepts of a function, polynomial function, and the zeros of the equation, and connecting that to the graph. And the graphs are going to get a little more complicated. Okay? One of the things you will have noticed is every polynomial function we've talked about in terms of graphs had single factors raised to the 1. None of the factors appeared more than once, and that's what's new today. That idea that factors can appear more than once is called multiplicity, and we'll get to that. So to begin with, imagine you're writing an exam and I give you this question, which I wouldn't. It's too simple for an exam. And I say, solve this polynomial equation. Well, let's just imagine something different. What if you were in Math 20 and I said, solve that equation? I probably wouldn't have called it a polynomial equation. I probably would have called it a quadratic equation. And I probably wouldn't give it to you like that, would I? I'd probably say, x squared minus 2x minus 8 equals 0. But you would factor it, and you would look at this, and you would say, x is equal to 4. And I would like somebody to explain why 4 is a solution. And the word why is important. The answer to that question is not because if you set x minus 4 equals 0, x equals 4. That's not why 4 is a solution to this equation. So why is 4 a solution to this equation? See, this would have been explained to you in Math 20, but then you just get in the habit of saying, oh, if it's x minus 4, x equals 4. The reason is 4 makes x minus 4 0, and x minus 4 is a factor. So how I would explain this in my Math 20 class is I would say, if that's 0, I don't care what x plus 2 is, because I'm going to take 0 times x plus 2. I'm going to get 0, which is what I need to get. Another solution would be x equals negative 2, correct? Why is that the case? Because if x is negative 2, then this factor that I've underlined is 0, so it doesn't matter what the second factor is because factors multiply. So x minus 4, whatever it is, times 0 will still give you 0. Well, listen, all we're doing is expanding our horizons here. Instead of having 2 things multiplied together, we have 4. If any of those 4 are equal to 0, the whole thing will be equal to 0. If this is 0, then it doesn't matter what anything else is because you're going to take 0 times the other stuff. Are you with me on that? So to solve a polynomial equation that's factored, you simply say this. It's simple. It's just the same idea with factorable quadratics. By the way, if it's not factorable, we don't have a quartic equation that you can throw A, B, C, and D and E into to solve for x. Anyway, we solve this. We get x equals 1/2, x equals negative 3, x equals 4. That, of course, should say x minus 4 is equal to 0. And then we also have x equals negative 2. Does anybody have any questions with the answer to this example? Okay. We're running around in circles now because we've talked about this again and again and again. The zeros of the factors are the numbers that make the whole polynomial 0. The zeros of the factors are the numbers that will be the x-intercepts of the function. The x-intercepts of the function are the zeros of the factors. The bottom line is when you compare this and this is an intuitive thing. Well, not really intuitive. I don't know that you need to write all this down. When you compare this function, the question says, what's the relationship between the zeros of this function and the solutions to this equation? They're the same. Because, if I say, what are the zeros of the function, I am asking you to solve this equation. It seems as though it shouldn't even require an explanation. If I ask you for the zeros of this function, also known as the x-intercepts, then what you do is you change y to 0. And now you've got the equation, right? If, on the other hand, and this is a little sneakier to think about, if I say solve this equation graphically, then what you're going to do is you're going to imagine that this is y and find the x-intercepts. So the bottom line, and I think it is important that you can understand how to communicate why they're equal, but that's not as important as knowing that they're equal. The zeros of the function are equal to the roots or solutions of the equation. And again, I believe this came up yesterday. It's why in high school math, even textbooks don't often use these words right. Solutions and roots apply to an equation. Zeros and x-intercepts apply to a function. But they're all kind of the same thing. They're all just mixed around in the same bowl. Now, I have a question for you, though. What if I said solve this equation? Well, you know what you'd have to do? You'd have to factor it. You'd have to use all of your mathematical skills to factor this. Now, maybe if it's a machine scorable question like a multiple choice or a numerical response, you can cheat and do it on your calculator, right? But otherwise, you'd use synthetic division and the factor theorem. And I will tell you right now that if you did factor that, you get the equation that we were asked to solve. So now we're talking about an exam question. I wouldn't say to you, solve this equation. I would say, solve that equation. Remember, for written response, you're expected to be able to factor up to degree 5. I would say, with an equation on a written response, degree 5 is pushing it because after you factor it, you still have more work to do. But I think solve this polynomial equation not graphically, algebraically is a legitimate written response. By the way, you would just set all of these equal to 0, right? We've already solved it, so you don't need to write anything here. All right, sketch each graph using a graphing calculator. This is the big thing. Now, I'm not going to use a graphing calculator, and I don't want you to unless you want to. I have these graphs loaded up in my graphing program with window settings that allow us to see the important features. But before we do this, before I show it to you, I hope you would agree that the x-intercepts will be -1, +2, and +3. And we're actually now talking about applying what we just learned or talked about in example 1 to this. Because x-intercepts are found by setting y equal to 0. And will you forgive me that I don't write x plus 1 equals 0, and then -1, -1, x equals -1? We know how to solve mentally these very basic factors. So what we do know, and we can put this on paper now before we look at the graphs, is that at 3, there will be an x-intercept. And there will also be an x-intercept at 2, and there will also be an x-intercept at -1. We know this, and by the way, everybody here should be able to sketch this one without a calculator. Because if you expand this out, if you write it in expanded form, it's going to be f of x is equal to x cubed plus some stuff plus 6. And to make my point, you don't even need to worry about the plus 6, which is the product of all of the constant terms. The fact that when you expand it out, you get positive 1 x cubed means it's an odd polynomial function. And Paige, this is kind of related to your question yesterday. This is a cubic function. Does it have to have 3 factors, Paige asked me. And I said, well, it doesn't have to, but everything we've learned so far points in that direction. Okay? But it's odd, which means the arms are in opposite directions. One arm is down, one arm is up. And more specifically, the right arm is up because the leading coefficient is positive. There is only one way you can draw this John Travolta shape with the right side from your perspective up and the left side down, so it goes through these points. If it looks like this, it has to start down here and finish up here. So how can you possibly draw a curve, and it doesn't have to be perfect, so that it goes through those points with that condition? Well, it's going to come up through here. It has to change direction because it has to come down through this point, and then it's going to change direction again fairly quickly. And I made a slight error in my drawing there right here, and it's because I stopped drawing. When you stop, your arm is already moving in a particular direction. You stop, your brain can't match that direction perfectly when you start again. So my recommendation is always look ahead and just draw the smoothest curve you can. We should have arrowheads on the end of each of these. And that's what the graph should look like. And in order to, let's say I was writing a written response, in order for me to kind of fix my errors, you know what I would do? I would do that, okay? And then I can put -1 here, 2 here, and 3 here. Well, let's take a look at what the graph actually looks like. This is what the graph looks like. We were bang on. You cannot tell by doing what we're talking about here how far up vertically and how far down vertically it goes. But it has the right features. The arms are in the right direction. The x-intercepts are nice and clean. Any questions with that one? So you could do this on a graphing calculator if you like. Now, what's different about this one? And I want to keep bringing up what Paige and I were talking about yesterday at the end of the class. If we expand this out, we're going to get an x to the 4. Because what this polynomial function says is f of x equals x plus 4 multiplied by x plus 1 multiplied by x minus 3 multiplied by x minus 3. So this, if I expand it out, will contain an x to the 4 plus some stuff, plus it doesn't really matter for today, but we can calculate the constant term by multiplying 4, 1, -3, and -3, and getting 36. I want to talk about the language here because I think it's really important. This is a degree 4 polynomial. Does it have 4 factors? Yes. 2 happen to be the same, but it does have 4 factors. Do degree 4 polynomial functions always have to have 4 factors? No. Here is an example in factored form of a polynomial function that has 3 factors, and it's degree 4. Right? The reason why this doesn't have 4 factors is because one of the factors is quadratic and you can't factor it further. So what I had answered yesterday when we were having this discussion is, yes, a degree 4 polynomial function will have 4 factors if they are all linear, if they all have x to the 1. But we would still say 4 factors. So would you agree the x-intercept should be -4, these are x-intercepts, -4, -1, and 3. Okay, so we can plot those in here. -1, -2, -3, -4. You don't have to be an artist, but try to make those equally spaced. And then, let's see, -1, and 1, 2, 3. I'm just going to need a little bit more room here. Now, the leading coefficient is +1. If we were to expand this, it's +1 x to the 4, which means putting the positive with the degree 4 together, both arms are up. Even degree means right arm is up. Positive leading coefficient means right arm is up. Even degree means they're both in the same direction. So this function is going to start up here, and it's going to finish up here. That's the end, what we call the end behavior. But how are we going to draw this so it does that? Well, we don't know yet, but let me show you what the graph looks like. It looks like that. The graph comes down through -4, turns around, goes up through -1, starts coming down, and 3 is an x-intercept, but it doesn't go through it. It can't go through it because if it were to go through it, then it would have to come back up and there would be another x-intercept. So it's like it's going to go through, but because x minus 3 is a factor that occurs twice, it changes its mind at the last minute. So this is what it looks like. It comes down through here, changes directions, goes up through here, comes down, and nice and smooth, do that again, comes down, up, down, nice and smooth. It does that. It doesn't have to be perfect. You could draw it that way. You could draw it this way. I don't care. What is important, everybody, is that these two x-intercepts are what I call clean x-intercepts. Nice and smooth and clean. There's nothing funky going on with those x-intercepts. But this x-intercept is not a clean passage. It's not even a passage through the x-axis, and this is called a tangent. Nothing to do with trigonometry unless you get into calculus and you start talking about slopes of tangents and all that stuff, okay? And what we're learning here, everybody, is that it is this 2 that produces the tangency. We say the curve is tangent to the x-axis at that point. It just touches the x-axis. Any questions with B? All right, C. Well, I probably shouldn't have to write this out, but if I do, and if you do, you should know it will be x to the 4 plus a whole bunch of stuff, right? Because this is really x plus 1, and then times x minus 3 times x minus 3 times x minus 3. If you want, there is some filler in here in this polynomial sandwich, and then it is minus 27. So the y-intercept is negative 27, but that's not helpful in drawing it. I don't even want you to look at that, really. I hope you agree the x-intercepts are -1 and +3. The graph is going to go through -1 cleanly. And if I go back to this example, I can demonstrate something to you, that the exponent on the x plus 4 was 1, and the exponent on the x plus 1 was 1. That's what produces a clean passage through the x-axis. If the exponent is 2, you get a tangent. 3, you don't get a tangent. 3 is not 2. What do you get? Well, let me show it to you. You get that. So, first of all, looking at our graph and the fact that it starts with positive x to the 4, do you agree both arms have to be up? It's positive 1x to the 4, so positive 1 says the right arm is up. It's an even degree, so both arms are up, which means the function has to start here and finish here. And we've already kind of established that it's going to be nice and clean through this. But what happens is, and this is kind of hard to put into words, but a clean passage, let's say this graph were curving up towards 3. A clean passage would be just a regular, nice line going through. A degree 2 on the factor means it's heading towards that 3, and then it changes its mind and goes back down. This is like it changes its mind twice. This is like it knows it's not going to go through cleanly, so it starts to change direction as if it's going to start going down again, and then at the last minute, it changes direction again. And it has this nice curve to it here, where the curve to the left of 3 is shaped like an umbrella in the rain, that the water would run off of it. But to the right, it's shaped like a bowl sitting out in the rain. Half of a bowl, anyway. So this is what it looks like. It comes down nice and clean. It goes up, and you're going to struggle with this. You are expected to draw these on written response. You have to have that shape where it's going up, and it starts to change direction like this. And then when it gets here, it changes direction again. It has to have that wobble. You would not be able to tell how severe that wobble is without technology. In other words, that is fine. Excuse me. This is fine. As long as they go through x equals 3 and there's that wobble or kink or twist in the curve. And this, I'm going to get rid of the green one and just go with the red. This, of course, is a clean x-intercept. But this is called an inflection point. It's a point of inflection. Good? I mean, we haven't really come to any kind of conclusion yet, but we're about to. This one. Well, let's just try this. Without using technology, would you agree there should be an x-intercept of 3? Cyrus, will that x-intercept of 3 be clean, a tangent, or an inflection?
Clean.
Clean, because it has an exponent of 1 on the factor. So this should be clean. Clean is just the word I use. Tangent and inflection are math terms. Clean is just a word for me to describe it. It will have an x-intercept of -4. Cyrus, will the -4 be clean? Will be tangent?
No.
It will be an inflection because the exponent is 3. Perfect. And then we will also have an x-intercept of 0 because 0 is the number that makes that other factor x 0. And since it's raised to the 2, it will be tangent. And I'm not setting you up for failure here. I've taught you everything you need to know, almost. In other words, there's no tricks here. What we learned about degree 2 and degree 3 are the same. So an x-intercept of -4, -1, 2, 3, 4, and it is going to be an inflection point. I just do that so I can keep track of things. It will have an x-intercept of 0, and this will be a tangent point. It will have an x-intercept of 3, close enough, and this will be clean. If you were to expand this out, you would get an x to the 6. Because, and I will write it down and then immediately erase it, it's going to be x minus 3, x plus 4, x plus 4, x plus 4, x. So, by the way, there is no constant term. The constant term will be 0 because of that factor of x. But if we count up these linear factors or multiply the x's, you get x to the 6. You don't have to do that anymore. It's the sum of all of the exponents on these linear factors. So, since it starts off with x to the 6, which is a positive term, the right arm is up. Since the degree is even, the left arm is up. It has to start in quadrant 2, go down through -4 with a twist, with an inflection, then go up towards the origin, but change its mind so it's tangent at the origin, then change direction again and go up cleanly through 3. So it's going to look, it's going to come down. I have to anticipate what's happening here. I can't just go down and then go, oh, it has to inflect. I'm already anticipating the change in the direction of the road, so to speak. It's going to come down like this and then change direction again. So it's going to come down. And now it has to smoothly change direction again to go up here, but it's going to be tangent, and then it has to go cleanly through. There is no way, without making a table of values or graphing it on a calculator or a computer, for you to decide how low these minima go. That's what it's looking like. Now let's take a look at the graph. Same features. This one, which is the true graph, goes down a lot further between 0 and 3. All right, so let's put this all together. The remainder of the lesson should not take very long. We've set things up. Some of the factors in these examples occurred more than once. Specifically, if you look at some of them, they had a factor, I think it was x plus 4 cubed. Is that right? In the previous one. And the fact that those occur more than once is called multiplicity. Multiplicity is telling you how many times a factor occurs in a polynomial when it's in factored form. So for example, this is the one I think we just did, right? There is a factor of x minus 3 with a multiplicity of 1. That also means there's an x-intercept of 3 with a multiplicity of 1, which means a clean x-intercept. There is a factor of x plus 4 with a multiplicity of 3. So when you see that phrase now, this phrase that I'm going to highlight, you should know that in the polynomial when it's in factored form, there's x plus 4, x plus 4, x plus 4. And in that same polynomial, x is a factor with a multiplicity of 2. And the corresponding x-intercepts have those multiplicities. The multiplicity of the x-intercept of -4 is 3. Example 3 is asking us to summarize things. And what I am telling you in this, let's just cut to the chase, that if the multiplicity is 2, we know it's tangent. It turns out if it's 4, it's tangent. If it's 6, it's tangent. If it's 8, it's tangent. So any even multiplicity for a factor at a particular x-intercept will look like this. It will be tangent at that point. I feel as though we want to be technically correct here. 0 is an even number. But if you had 0 for a multiplicity, then there's no x-intercept. Negative 20 is an even number, but polynomials don't have negative exponents. We know that if it's a multiplicity of 1, it goes through wherever that x-intercept is, it goes through cleanly. Nice smooth curve. You're just relaxing as you're driving around a curve. You're not yanking the wheel back and forth or changing direction. You're just following a curve. And we know, and I'll just put the x-intercept here this time, that if you have a degree 3, it's an inflection point, but I'm telling you it's also an inflection point if it's degree 5 or 7. So this is clean. This is tangent. And this is an inflection point. And finally, before we just try a few examples, without even looking at calculators or programs, if you ever see this curve on the right, and you're asked to find the equation of the function, we would always assume it's 3. You always assume the smallest degree. Otherwise, there's no right answer. If you're wondering the difference between degree 3 for a multiplicity and, say, degree 5 would be more severe. It would be a more twisty change in direction, and then changing again. So, without using a graphing calculator, sketch the graph of these. And your assignment is going to be to sketch some of these, but it's also going to be able to look at the graph and come up with the equation. Well, we're going to have an x-intercept of 1 with a multiplicity of 1. Because there's an x minus 1, and the multiplicity of it is 1 because the exponent is 1. X plus 3 is going to give us an x-intercept of negative 3, but it will be a multiplicity of 2 because it's x plus 3 squared. This is really simple once you get the hang of it. Well, you know, I want to be careful here. The final one has a multiplicity of 1 because there's just an x plus 2 to the 1, and the x-intercept is negative 2. It's easy, but you have to slow down and keep your thoughts organized because you're dealing with 6 numbers here, and they all mean different things. So we have an x-intercept of negative 3. We can scale our grid so that we have a negative 3. We have an x-intercept of negative 2. There's another one there, and an x-intercept of 1. And if you were to expand this out, your leading term would be that. Is everybody in agreement? I already mentioned this. It's the sum of the exponents, but now I can use different language. The degree of the polynomial is the sum of the multiplicities, if they're linear factors, right? If you have that quadratic factor, that you got to think a little bit more. So both arms are up. Negative 3 is tangent. Negative 2 is clean. And 1 is clean. I'm just putting these words here so I can use them, so I can make sure I don't make a mistake. My graph may very well cut through some of those words. If it's tangent, I know that some of you are not confident or that good maybe at drawing. So maybe just with a pencil lightly, just maybe do this because you know it's tangent there, right? And it's clean here, so it's got to go through here. And it's clean here, so it's got to go through there. And maybe that kind of gives you some guidelines to follow, a road to look at driving through. So when I put them together, it curves up, it's got to change direction and go down, and then it goes up clean. Good enough. If you wanted to graph it on your calculator and see how close you are, that's fine, but that's good enough. There will be an x-intercept at 3. There will be an x-intercept at -1. There will be an x-intercept at -2. And I'm just, in my head, I'm saying, let's not write that down. And then I'm saying, no, let's write it down. Let's not try to do too much in our head. The x plus 1 tells us we have an x-intercept of 1. The fact that it's to an exponent of 1 means the multiplicity is 1. The x minus 3 tells us we have an x-intercept is -1 with a multiplicity of 1. The x minus 3 is an x-intercept of 3 with a multiplicity of 1. The x plus 2 gives us that for an x-intercept, -2 with a multiplicity of 2. So we're dealing with clean tangent. At -1, it's clean. At 3, it's clean. At -2, it's tangent. Yeah? Oh, thank you. 3. It's an inflection point. What is, well, interesting is maybe the wrong word. I guarantee you that if you make that mistake on an exam, I guarantee this is going to happen, that when you say to yourself, that this is x to the 5, and I hope you can see that it will be positive x to the 5, and you say to yourself that it has to start here and end here because it's x to the 5, if you put tangent for this, it's impossible to draw. So had I thought it was tangent, if I tried to draw it, I'd get to the end and be going in the wrong direction. So it has to be an inflection here, and thank you for that page. It has to be an inflection here. It has to have this shape. It has to come down through here and up through there. So you have to kind of plan ahead. We'll draw a curve and then change direction and come down and then back up. Any questions with B? C, 2 tangents and a clean. The x-intercept of 1 will be tangent. I'm not going to write the multiplicity here. I'm just looking at it, and it's an exponent of 2, which means it's tangent. The x-intercept of 3 will also be tangent. The x-intercept of -5 will be clean. Again, we're looking at the exponents to determine the multiplicities. An even multiplicity is tangent. -5, -1, -2, -3, -4, -5. I scaled it by looking at the -5 first because it's the bigger number in the left direction. And then we also have at 1 and at 3. Putting everything together, this is clean, this is a tangent, this is a tangent. It has to start down here in quadrant 3 and end in quadrant 1 because when we expand this, we're going to get positive x to the 5. Or the sum of the multiplicities is 5 and the leading coefficient will be positive. How are we going to do that? Well, listen, if it comes up cleanly through here, and again, you can lightly with a pencil just kind of do that cleanly through there, but it must be tangent here and tangent here, then it has to come tangent to this point at 1 and up and then change direction. And I don't even think when I draw it, I should go up as far as I drew it here. I should probably just draw this.